Section 6.1, Verifying Trigonometric Identities. An identity is an equation that holds true for all values of the variable. Let's consider the following equations. X plus 1 equals 4. Well, that's true for x equals 3, but it's false for all other values, and therefore it's not an identity. X plus 5 equals x plus 2. Well, that's never true, so that's certainly not an identity. Notice that if we were to subtract x from both sides, we would get 5 equals 2. That's never true. 7x plus 3x equals 10x. That's always true, so that is an identity. If you were trying to verify this as an identity, you might notice that since the right side is 10x, the left side, using algebra, simplifies to 10x, so that's always true. Now let's look at trigonometric identities. A trigonometric identity is a trig equation that holds true for all values of the variable. Let's consider these equations. Sine of x plus 10 equals cosine of x. This is never true, so it's not an identity. We can see that it's never true because the sine of x oscillates between -1 and 1, so if we add 10 to that on the left, that left side is going to oscillate between 9 and 11. And it's going to equal the cosine on the right, which is going to oscillate between -1 and 1, so they'll never be the same. Tangent of x equals cotangent of x. Well, that's sometimes true, and it's sometimes false. For example, the tangent of 45 degrees equals the cotangent of 45 degrees, but the tangent of 30 degrees does not equal the cotangent of 30 degrees. So that's not an identity. Finally, this equation is always true, so it's an identity. You're not expected to be able to see that by looking. We're going to verify this identity in this lesson. To do that, we're going to need to recall our fundamental identities. The reciprocal identities involved sine and cosecant being reciprocals of each other, cosine and secant are reciprocals of each other, and tangent and cotangent are reciprocals of each other. The quotient identities, we have tangent equals sine over cosine, and cotangent equals cosine over sine. For the Pythagorean identities, there's one that involves sine squared and cos squared, one that has tan squared and secant squared, and one that has cotangent squared and cosecant squared. And we'll be using these to verify our other identities. To verify an identity, we'll show that one side is identical to the other side. We manipulate each side independently of the other, and we'll start with the more complicated side. We'll use our fundamental identities until we can show the two sides are identical. This first example is the equation we saw earlier, and we can verify it using sines and cosines. We'll start with the more complicated side, which is the left side, and then we will look at how to change cosecant and tangent to sines and cosines. Recall that we have these fundamental identities, and this is the left side of the identity that we're working with, and we're trying to change cosecant and tangent in terms of cosines and sines. The cosecant is 1 over sine, and the tangent is sine over cosine. So we can write this as 1 over sine times sine over cosine. Then we can cancel the signs, multiply straight across, and then we notice that the cosine is reciprocal with the secant, so 1 over cosine of x equals the secant of x. We have now verified this identity. It's considered verified because we took the left side and did the algebra to obtain the right side. And the strategy that we used was changing to sines and cosines. Now let's consider some general guidelines. We work with each side independently, starting with the more complicated side. We look for opportunities to use our fundamental identities, and we have various techniques that we can use. We saw an example of using sines and cosines. We'll also see an example of how we factor out the greatest common factor. We sometimes need to break a fraction up into 2 or more fractions. This can occur when we have a monomial in the denominator, and so we can do a plus b over c is a over c plus b over c. This also works with subtraction. Sometimes we have to combine our fractions, and sometimes we have to multiply the numerator and denominator of a fraction by a binomial that appears on the other side. Don't worry if you hit some dead-end streets. Sometimes you have to start over with a different strategy. For example 2, we will use factoring to verify an identity. notice that we will start on the side that's more complicated. That's the left side. We take a look at it and we notice that the sine of x is common to both terms. So we can factor out that sine of x. When we factor it out of the first expression, it leaves just 1. And we factor it out of the second, it leaves negative cosine squared of x. Now we should notice that we have a trig function squared that's added to or subtracted from 1. And that reminds us of fundamental identities that are the Pythagorean identities. The one that involves cos squared is sine squared plus cos squared equals 1. If we transpose the cosine squared, then on the right side we get 1 minus cosine squared of x, and that equals the left side of sine squared x. So we can make that substitution here, and now we have the sine of x times the sine squared of x. Sine to the first power times sine to the second power is sine to the third power. And we have verified this identity because we started with one side and obtained the other side. In example 3, we're going to use the technique of combining fractions. We'll start with the more complicated side, and to add these fractions we need a common denominator. So we'll need the sine of x times the binomial 1 plus cosine of x. So we rewrite the fractions. The first denominator needs the sine of x, so we write that on the bottom and on the top. The second denominator needs the 1 plus cosine of x, so we write it on the bottom and on the top. We'll be able to combine these fractions, but first let's do some simplification. Sine x times sine x is sine squared x, and to multiply out these two binomials we'll use FOIL. 1 times 1 is 1. The outer gives us 1 times cos x, so that's cosine of x. The inner is also cosine of x. Cos x plus cos x is 2 cos x, so we write that coefficient of 2 in. And then finally, cosine times cosine is cosine squared. We're going to need more room for this problem, so let's put the identity we're verifying up above. And then we'll take the result we have so far and move it to the top. We can combine these two fractions into one fraction. We put the sine squared plus the other numerator, and now we're just going to bring the cosine squared close to the sine squared, and then we can recognize that the sine squared of x plus the cosine squared of x is equivalent to 1 using our Pythagorean identity. And since 1 plus 1 is 2, we add those together, and then we'll take this result to the top of the next page. In our numerator, we notice that the 2 is common, so we can factor that out. And then we see that we have the same binomial on the top and the bottom, so we can cancel both of those. And that leaves us with 2 over the sine of x. We can then factor that 2 out, and since 1 over the sine of x is equivalent to cosecant because of our reciprocal identity, we can write this as 2 cosecant of x. So we have verified this identity because we started with the left side and we did algebraic manipulations to show that it is identical to the right side. In example 4, we'll see that sometimes we end up needing to work with both sides of an identity. Let's write our identity up top because we need all the room we can get, and let's begin working with the left side. To simplify the left side, we need to get a common denominator, which will be the product of those two binomials. We rewrite our fractions, leaving room. On the first fraction, we need the 1 minus sine theta, so we write that on the bottom and the top. And in the second fraction, we need 1 plus sine theta, so we'll put that down on the bottom and up on the top. We can now add our numerators. The first fraction is 1 minus the sine theta, and the second one add 1 plus sine theta. This simplifies to just 2 because 1 plus 1 is 2, and the negative sine theta plus sine theta cancels out. We can then multiply those factors in the denominator. It's technically FOIL. 1 times 1 is 1. The outer of minus sine x and the inner of plus sine x canceled out, and the last gave us a positive times a negative, so we got negative sine squared theta. Whenever we have a trig function squared added to or subtracted from 1, it's good to look at our Pythagorean identities, and sine squared plus cos squared equals 1. If we transpose the sine squared, we get 1 minus sine squared equals cosine squared, so we can make that substitution. This is what we've obtained so far working with the left-hand side. 2 over the cosine squared of theta might feel like a bit of a dead end if we're trying to obtain the right-hand side of 2 plus 2 tan squared. Because what we have so far is now more simplified than the right-hand side, it's common to leave that alone for a moment and consider working with the right-hand side. If we take our right-hand side and factor out the 2, then that will leave us with 2 times 1 plus tan squared. We mentioned before, when we have a trig function squared, that it's a good idea to consider our Pythagorean identities. And in this case, we have 1 plus tan squared equals secant squared. So let's take that back to our problem, and we can make that substitution. 1 plus the tangent squared is the secant squared. At this point, we have 2 over the cosine squared on the left-hand side and 2 times the secant squared on the right-hand side. Commonly, when we have trig functions squared, we go to our Pythagorean identities. But since cosine and secant are related as reciprocals, we'll use the identity of secant of x equals 1 over cosine x, because these can be raised to any power. We'll square both sides, and we can replace the secant squared with 1 over cos squared. We then multiply that out, and that gives us 2 over cosine squared. So we have verified this identity, because the left side is equal to the right side, which both are 2 over the cosine squared. To verify this identity, we simplified each side independently, and we obtained the same expression.